Okay.
Well, good morning, everybody. I'm Don Proeschel. I'm a Director of Corporate Relations at UT Dallas, and my focus is on UTDesign Capstone Projects. Well, it's good to be here, and I am excited to talk to you about UTDesign Capstone Projects. It was about 9 years ago that I was working in a software modeling and simulation company called No Magic, and we actually sponsored a computer science capstone team that won first place. How cool is that? So now that I've been at the university for nearly 5 years, we are blowing and going. And the way I want to introduce this is let's start with an overview of the program. So let's watch this first video.
Okay.
Whether you're an entrepreneur or part of a top 100 company, chances are you have more projects piled up than you can handle. You would like to work on other projects, but can't allocate resources and time without larger projects falling behind. There's just not enough to go around. What if there was a way to tackle this problem without overspending and sacrificing productivity, all while still getting the results you want? Meet UTDesign Capstone. At UTDesign Capstone, senior undergraduate students from all types of engineering and computer science disciplines come together to work on a project of your choice, helping you save time and resources. Here's how it works. You come to us with a real-world problem, and a team of senior design students will work to complete this project as the pinnacle achievement of their undergraduate curriculum. As a corporate sponsor, you play one of the largest roles in UTDesign Capstone projects. A chosen corporate mentor from your company will serve as the technical point of contact for the project. A UT Dallas advisor will assist the corporate mentor and provide guidance to the team members as they execute the project for you, our customer. Our students will work together to build prototypes, computer programs, or simulation models, depending on the project field. At the end of the project, students will present a final report along with test and evaluation results to accompany their completed project. And the best part is that it all belongs to you. As part of the UTDesign Capstone program, your company retains full ownership of the results from the project. Your guidance and sponsorship will help give students real-world experience to prepare them for the future. Who knows? Maybe they'll even work for you someday. So what are you waiting for? Let us find creative solutions for your next project here at UTDesign Capstone.
Well, this little gem of an animated video was created by another department at the university called at the time Arts, Technology, and Emerging Communication, was renamed at the fall of this year, Arts, Humanities, and Technology, AHT. So it's a blend of people with creative ability and technical ability, and we think they knocked it out of the park. It's our best marketing tool in our marketing toolbox. Okay, let's now take a look at a project that we did for Texas Instruments.
My name is Mark Simpson. I'm an equipment engineer. I work for Texas Instruments, DMOS 5 here in Dallas. And we came to UTD because we've worked with them before. And we asked them to design us a lifting system to help us with the maintenance of some heavy equipment down in the fab where we make chips. And these chillers is what we call them. And they're about 150 pounds and they're located underneath the floor. And it's actually supporting equipment to the big equipment that makes the chips. And they're very maintenance intensive. And so we were lifting them out by hand and having to lift them up halfway out of the floor and disconnect hoses and wires and then finish lifting them up. And it's really a lot of work. So we've had interns work, some interns work on this project before. They hadn't really came up with anything. Simply because the summer interns are only there a few weeks and wasn't really enough time to come up with a good design. So we've asked the Mobile Lift team at UTD to work on this. And it was a 2-semester project, and we've had them on site several times to show them the problem. And they really exceeded my expectations. I had some doubts at the beginning, but they really came through and impressed me and did a really good job designing a lift system that's going to really help us in our job. And it's going to be a real world solution to a problem that we've had rather than just some prototype, something that you're gonna shelve it and never use it. We're gonna actually start using this thing next week. It's something we really need pretty bad, and we're gonna actually build a second one to use in our other fab. And then if it really turns out it's a really good, helpful thing that we can use, then we're gonna start building them for the other fabs around the world.
Okay, so this is actually version 2.0 of this video. You heard him saying we're going to start using this next week. The photographs that you saw are the system actually in use in their wafer fab factories. So is it important to keep the semiconductor wafer fab equipment running? Well, if you're making 100 million chips a day, yes. So this helps them to keep the chillers maintained, which helps keep their semiconductor manufacturing equipment operational. I'm now going to give you a brief overview on our UTDesign Capstone program. What this is, it's a partnership between industry and education. We do a few projects for government agencies, municipal, state, and federal, but 95% of our projects are with commercial companies. We've had over 400 companies that have sponsored over 1,200 capstone teams, and we've won 10, count them, 10 national first place awards with our projects since 2014. We now have 43,000 square feet of space in our design studio. I like to call it our acre of awesome. Next slide, please. So a capstone project is a requirement in the United States for all accredited universities that offer engineering and computer science. How that is done at the university is up to each university to figure out. The bar is actually set pretty low. We are light years above that bar, as you'll see. What the teams do is they define, design, build, and test a problem solution. And our goal is to provide at least 80% of the student projects with a project sponsored by a corporation or a government entity, filling in the rest with some student entrepreneur projects and some faculty projects. Our computer science students do a 1-semester project. Our engineering students do a 2-semester project, the first semester of which is the design phase, and the second semester is the build and test phase. What's fairly unique among our at UT Dallas among universities is that all results of the project are owned by the sponsor. So the students will sign over all their rights and you get to keep all of the IP. Next slide, please. So the student team is supported by a UT Dallas advisor who acts as a coach who meets with the students once a week to guide their progress, to make sure that they're meeting all their stage gate goals. The corporate mentor has to be knowledgeable in the field that he's overseeing, meets with the students for perhaps an hour to an hour and a half a week, answers a few emails. We have 4 UTDesign faculty directors. The least amount of time with the program of the 4 is 7 years. So it's 7 years and up. So we have tremendous stability in the program. And then we have a world-class support team that keeps things running behind the scenes. The 4 areas that we do projects in are biomedical engineering, mechanical engineering, electrical/computer engineering, and computer science, or any combination of these needed to deliver the solution to the customer. And again, that's fairly unique. Universities such as UT Austin do single discipline projects. It's either EE or it's ME. Never the twain shall meet. Well, that's the reason why we've won 10 national championships and they haven't. Just saying. All right, next slide, please. So here's our triangle of success. Keep tapping on it a little bit. There you go. So all 3. Keep tapping.
More.
There we go. All right. So here's our triangle of success. We have to have a project that's scoped to the talents of our students. We like to say these are engineering seniors, not senior engineers. They have lots of nice, bright, shiny tools in their toolbox that they have admired but maybe haven't used much. But with some guidance and the fact that these students averaged 1420 on their SATs when they came in. So you're starting with some pretty bright kids, and we give them a great education. And we get great projects from our sponsors, stir it up, mix it in with some hard work, and great things happen. So what we want is a project that's real, interesting, impactful, but not necessarily critical path. Oh, let me talk about the other two legs of the triangle. So we have a right size scope project, a corporate mentor that I just talked about, some resources that I'll show you on the next slide. It's a team of 4 to 6 students working an average of 10 hours per week each. What we like to give them is an MVP project with 2 or 3 stretch goals for our overachieving students. Next slide, please. On the left, you can see some samples of projects that we've done for large companies. Some of them are engineering, some of them are computer science. In the upper right, you can see we have a nice mix of startup companies, mid-sized companies, and large companies. Our sponsorship fee, we like to say, we'll give you a team of brilliant students for less than the cost of one intern. So our computer science project for 1 semester is $10,000, but wait, give us your project proposal a month before the semester starts, and we chop $2,000 off. So now you're talking about $8,000. For engineering, 2 semesters is a total of $15,000 or $13,000 if you get your proposal in a month early. Now that $13,000 also includes, it pays for up to $3,000 of parts, materials, and fabrication expenses. Next slide, please. Here is a sample of a project I got to see presented at Rochester Institute of Technology, sponsored by Texas Scottish Rite Hospital. We had a team of mechanical and biomedical engineers invent an implantable medical device to resolve a rare hip disease in children. This project was one of 20 presented at that conference, won first place in the United States. And a patent has been applied for it, and all the names of the students are on that patent application. Next slide, please. So our program is growing and growing and growing. In 2010, we had 25 capstone teams only in electrical engineering, computer science. This last year, we had 245 projects. We're projecting this academic year is going to be 275 projects. And in a couple of years, we're going to blow through 300. And remember, we need sponsors for 80% of those. So as that number grows, people like me have to run faster and faster. At my age, I'm going in the other direction. I'm just saying. I can still run an hour and a half. I just don't cover as much distance as I used to. All right, next slide, please. Oh, I'm sorry. I wanted to point out that the growth is mostly driven in computer science, where we doubled our undergraduate population between 2017 and 2021, and we are now the second largest computer science department in the United States. Next slide, please. Okay, so here's our 10 national first place awards since 2014. The National Capstone Student Competition is every 2 years. The top 20 of the best projects in America from the best universities are presented. The last 4 times this conference was held, we've taken first place in the United States. We actually hosted the conference this year in June. We were going to host it in 2020, but this thing called COVID happened. We had 68 universities in attendance. For the first time, we had 3 national finalists out of the 20 projects, and one of those 3 took first place. Now, remember, we didn't even have a mechanical engineering department until 2009. Our biomedical engineering department was launched in 2011. So keep that in mind as I walk you through these statistics. So the ASME has a manufacturing science and engineering conference every year, and they have 8 national finalists. So how did we do in competition starting in 2015? Well, we took first place in the United States in 2015, 16, 17, 18, and 20. second place in the United States, 2019, 20, 21, and 22. I think we've done okay for a brand new department.
Wow.
And then our electrical and computer engineering, we launched a regional design showcase in 2019. We've taken second place all 3 times this year. I'm told we were a 10th of a point out of first place. So we've done pretty well in electrical engineering as well. Next slide, please. Okay, so what are the next steps? We would love to have any of you jump on the bandwagon with us. In January, we're going to be launching electrical / computer engineering projects and computer science. Now, computer science, we are beyond desperate for sponsors because if you can picture the pig and the python, remember I showed you how fast computer science was growing. Okay, these are all seniors now, and we're gonna have like 100 to 120 computer science teams of students saying, "Hey, I want a capstone project. I want to graduate." And so Cynthia Hine and I are sprinting to find sponsors everywhere to get these students a real world learning experience. We will start mechanical and biomedical projects again in May. We launch those in May and August. And in conclusion, I'd like to say that UTDesign Capstone is your engineering force multiplier. Those of you who've ever been in the military understand what a force multiplier is. It's how you beat the bad guys who have more of them, but you have your force multipliers to prevail. So at this time, this concludes my presentation on the UTDesign Capstone program. And now I'm going to introduce to you the real speaker. I'm just the warm-up act. Dr. David Lary has done some amazing research in his lab. I was privileged to take a tour of it a few months back, and I was just blown away. He's done lots of capstone projects with us. Our students are helping him to succeed in his research. And so I'm going to turn this over to Dr. David Lary.
So thank you so much for inviting me. I really appreciate it. So just as a factoid to start off, I see you call your IoT meet, but I don't know if any of you know that maybe about 30 years before the term IoT was coined, NASA was using something called sensor webs. So what I'm going to show you today is a set of examples that use sensor webs or IoT, whatever you'd like to call it. Really, I refer to it as sensing in service of society. And so, so many times when we talk about IoT these days, we have devices in our vehicles, our houses, across the city. But what I want to show you here is a set of 9 different Sentinel types, from satellites to wearables to autonomous robotic teams. And basically, they all have this one thing in common, that we want to make better decisions, help keep people out of harm's way. So the theme running through all of it is this sensing.
Move your mic just a little bit.
So what this event is that we see here is something we hope will.
It'll be up in just a second.
Yeah.
The wireless is.
So this is an event we all hope will never happen. It's actually, fortunately, a simulated bioterrorism event in New York City. And so the reason I'm showing this, and for so many of the IoT applications, is prevention is so much better than cure. So if we have systems in place before an event, it helps us tremendously, because when the event happens, we don't have time to implement it. And that's one thing I was really impressed with the city of Richardson about, that they had a COVID plan, a pandemic plan, before there was a pandemic. So this preemptive protection is the theme. So there's a few things I wanted you to notice about this. The plume is going down these street canyons and slowly lofting as the surface is warmed. And the way this simulation was done is that there was a LiDAR topography of all of these buildings. So a plane flew over, captured the exact geometry of these buildings. And then once that capability is done, a really detailed computational fluid dynamics model, which is often abbreviated to CFD, did comprehensive simulations from all different directions. And then that was used to produce what you might call like a smart lookup table version of it that could rapidly be accessed for any wind speed or direction environment at the location. So as well as when such an event happens, it being able to provide optimum evacuation routes, because you wouldn't want to be breathing a cloud like that. You have a very limited time to get out. The optimum route would be perpendicular to the plume. And so, you know, the plume is being blown by the wind. But in addition to giving you that information, it can also let you have optimal placement of your sensors, because however many resources we have, we'd normally always like a bit more. And so we can use those resources we do have to the maximum effect. So before I go for the rest of the talk, I wanted to briefly introduce you to the IQ that was mentioned. So this is a partnership between the city and the university. It's along Collins Boulevard. Actually, I spend quite a bit of my time there now. And it may be an interesting place for any of you that are interested to visit. There are 6 different sensors in there on the university side. And it's a very, like it's becoming a hive of activity. So object spectrum folks are there as well. And we're just, well, they are just about to deploy a LoRa WAN in the building and for around. So actually across quite a bit of the city now, we have a LoRa WAN network that we're using for our real-time sensors to fit in from everything from that previous application I showed you to many more. Okay, so we are very familiar and relieved that we can have responsive protection. So we either call the fire brigade if there's a fire, or an ambulance, or the police. But what I really want to do is preemptive protection. So to have actionable insights that can keep us in front of the problem. So much of what I'm going to show you here, actually, Special Forces, US Special Forces came twice to visit us, and just last 2 weeks ago, we went down to Fort Story to present our team things there. And we were really honored that we were the only team that had these 9 Sentinel types, from satellites to wearables to robotic teams, and across dense urban environments. And the people that were attending this were all the folks they call a CDRNE. So if there's a nuclear device, a chemical device, a biological device, they are the ones that have the unenviable job to try and defuse them and make them safe. So that really fits into this passion I have. I want to help keep people out of harm's way. Like, prevention is very much better than cure. So to help give a sense of the scale of it, the little schematic here with each of these Centurion hats, and they are the different types of Sentinel that we are using. So we've seen one of them, which is a simulation Sentinel, but all the others are observational Sentinels. And essentially what each of these are is some sensing element or elements that are wrapped with some software, so like a software-defined sensor that can work together to help provide actionable insights. Now, the reason you see the MINTS leaf there is we called our center MINTYS-AI, so that's one of the 6 sensors in the IQ. And MINTS is much easier to say than our very long title, but each letter in this it has a lot of meaning. So the M is actually multi-use and multi-scale. So I want to give you an example of why we need to look at things at multi-scale. So we've all been in or seen on the news a variety of hurricanes. And the one that I want to choose as an example for some specific reasons was Hurricane Harvey. So if you think about before the hurricane makes landfall, the big picture really matters. And we see that big picture from the satellites, from the weather radars, and the value of that information is we can have a pretty good estimate of where landfall is going to be. So the actionable insight there is who needs to be evacuated. But the minute it makes landfall, it's the hyperlocal information that matters. For example, if you live close to that shoreline, what is the slope of my street? Is the surge going to like flood my house? And in the case of Hurricane Harvey, there's all these oil refineries and chemical plants. And so the reason that was significant is that surge then flooded these facilities. Large amounts of volatile organic compounds got into that water, and there were some neighborhoods that were surrounded on 3 sides by this water, which was then outgassing, causing severe respiratory issues. But the folks living in those houses, they were living close to refineries and so on, they didn't have the resources to figure out what it was. So they were suffering from those respiratory issues. But when the cleanup crews come, they don't necessarily have the right remediation, the right protective clothing. So then that's further avoidable issues. And then when the remediation comes to clean up things and put them right, the same thing could apply. So imagine if we could have a robot team and we have like multi-robots that could go into an environment they've never seen before and rapidly survey it. That would be really useful. So we actually built a team like that. And so that's why some of the sentinels here, unfortunately, covered by the...
You can click hide and it'll go away.
That's great. Thank you. How do we...
You might need to reshare your, just pull up your slides again.
I'm here?
There you go.
Oh. Yeah, I'm not used to driving Google share. I apologize. So what we actually produced is a autonomous robotic boat which can go unmanned for 20 hours. And the reason we chose a boat as part of our team is the water the piece calmed down. So we also had a robotic aerial vehicle that from above was observing the scene, not just with a visible camera. So you and I, we all use our mobile phones a lot. We probably it's the prime device we use for taking photographs. But our cameras in here will have a red layer and a green layer and a blue layer that we combine to give our color image. But in our robotic aerial vehicle, we actually had a hyperspectral camera. So we had a stack of 591 images, each of a different wavelength. So each of those images essentially gives us a whole spectrum for every pixel. So a given component in the water or the land would have a unique signature. Now, if you think about streaming uses right now, one of the big ones is streaming video. That's like a main use of bandwidth. So that's with just 3 colors, and it's like a major use. Imagine now you have 591. You're not going to, even with 5G, 6G, and whatever the next 7G is, you're probably not going to be able to stream that. That's a really fat pipe. So what we actually do is each of the robots is on the same network. So when I worked at NASA and many space agencies, they produce global products for the planet, whether it's for the water, the composition of the water, or the land surface, or the atmosphere. And so, as this is the water example, for the water example, that would take about 10 years to gather the so-called training data for that. So what that training data would be is in situ measurements made by ocean-going scientific cruises. So this is not like your pleasure cruise with the Lido deck and so on. This is a much more austere environment where it's like a lab on the water. So they will make measurements of the composition of the water, and then they'll want happenstance overpasses of the satellite. So because the satellites, typically the ones being used for this, always they're in a polar orbit, and they always make observations at the same local time. So to have the satellite fly over just where the boat happens to be is relatively few occurrences. So the set of training examples is about 18,000 that would have been collected over 10 years. Our robotic team gathered that volume of data in 15 minutes. And then it was actually processed on board in real time. So when you have the satellite data and these products, so you, with the interesting global change, for example, you may have gone to look at, let's say, sea surface temperature or other products like that, that many space agencies make available. The way that works is the data goes from the satellite. When it goes over a ground station, you have the communication to the ground station. Goes from the ground station to the data center. That's where the number crunching happens, and then the product is disseminated. So the latency of that could be from a few hours to maybe a couple of days, depending on the version of the product and so on. Whereas in our case, it's processed on board on the edge in real time, and then our data product streams live. So it can learn a new environment it's never seen before, rapidly. But we don't just use that paradigm with our robotic team, we also use it for the wearable devices. So in fact, if you wanted to visit the IQ, you would see there's a mannequin there, and everything the mannequin is wearing is a wearable sensor, from the socks with pressure sensors to the shorts that every muscle activation is recorded and you can see these things live, to the shirt, and then also to the EEG with like 64 electrodes across the head, to eye tracking glasses that have 2 cameras on every eye. And so you may say, well, what are we using that for? Well, if you or I look up at a light, in a few milliseconds, we have an autonomic response that our pupils shut down. And you can actually film that. It's really pretty cool. So we're all familiar with the proverbial canary down a coal mine that would sacrifice themselves for the miner. All right, so that canary is a sentinel. And so my mantra is like, no canary has to die. Because imagine that we could decode our body's responses. And it turned out that we could actually do that. And I'll show you some of those pictures in a bit. So what we did is, at the same time as measuring everything we could in the air, we were also measuring 113 parameters from this wearable suit 500 times a second. We actually learned how to decode our body's response. So we could tell how many particles per cubic centimeter of a given size we were breathing just by our body's autonomic response. And then we did it for one individual over 7 different collections. Then we did it for multiple individuals. And for all of them, we could have one single machine learning model that learned their response. So for all of them, we could predict with a single model, the composition of the air just from our body's automatic response. So we're an amazing sensing machine. It's a wondrous thing, but we're not used to decoding our body's response. So our IoT, sensor web, whatever you want to call it, coupled with the machine learning in real time, can help us do that decoding. So whether it's for firefighters going to harm's way or the other special forces or whatever, as mentioning, this can be a real assistance. So the point that the reason I'm dwelling on this slide is I would challenge you in your IoT applications. You probably already have certain sensors or devices you use, but what if you use them together with a much wider context? So simultaneously, And I'll show you, I should move on from these. Simultaneously, for all of our sentinels, as well as them, each one measuring things individually. So yes, this is an example in some of the videos. So each of these different videos, like here, this is our autonomous robotic team. There's the aerial vehicle with the hyperspectral camera on it. Then this is the boat that was measuring the in situ ground truth. So the boat was streaming to the aerial vehicle the composition of the water, and then on board the aerial vehicle, there's real-time machine learning that turns this stack of 591 images into the composition of the water, for example, the crude oil content or whatever other sensors. So we had about 40 sensors under this boat measuring once a second, and also a sonar giving us the depth, the bottom type, the height of vegetation. So actually, if you're a fisherman, that would be your ultimate fish finder. And then in real time, it processes it on board and then streams the results. So you don't see it in here, but we had a U-Haul with a big screen on the back, and streaming to that was the data from all of these things and the map of, in real time, the composition of this. So imagine now you're responding to a disaster. You're the fire chief or whoever, the emergency management person in charge of responding to an environment. You can now have some actionable insights that can help keep your team out of harm's way and do the best response. So let me take one more example. We were all probably tracking Deepwater Horizon. So that is a really good example. So do you know that the ship's captain, because of their viewing geometry, they can't really see where the oil is because it's a glancing geometry, you can't see it. So the way it would work is there would be a trained spotter. So NOAA, the National Oceanic and Atmospheric Administration, they actually have a job which is a trained spotter for oil spills. And what they do is they estimate the thickness of the oil and the age of the oil and how weathered it is by its color. So imagine now they go out in a helicopter, they visually inspect, obviously with some uncertainty because it's a more subjective thing, the age and the location, and more importantly, maybe where the thickest oil is. They then radio the ship's captain to go to that place for, say, the skimmer ships, which are then trying to clean it up. But by the time the captain gets there, because the wind has carried on blowing, the oil has moved, but they can't see that. So then they collect it all together, and then often they set it on fire, which is actually more pollution than a really large city. So if you were to take this approach, the captain of the ship could launch his or her own aerial vehicle with this hyperspectral imagery and the machine learning. You could calibrate exactly the age, the type, and the thickness of the oil.
I have a question for you. So, how do you collect the data for those things? Whether it's a supervised learning or unsupervised learning?
We use all types of learning holistically together, and they each have a different role. So we use both supervised regression, classification, and unsupervised is really valuable for a larger number of these aspects. Sorry, I lost my flow.
The boat would go into the most thickest oil.
Thank you. So, so then the captain could know where the thickest oil is and go there, but then the robotic boats, not only can it be part of the in situ validation, they could also have these digesters that can digest the oil instead of having to set it on fire. So the point that I'm trying to make is this capability of multiple devices on multiple platforms talking to each other that you can coordinate is not just helping you to get better intelligence, they can also be part of inventive solutions. So the way I view all of these things is they are Lego blocks. that you can assemble them in different ways. So the software-defined sensors, which the boat has a suite of about 40 of them on, the aerial vehicle maybe had about 15 different ones on. They then hitch a ride on your platform, which gives them power and communication. And so then these can be assembled to address whatever issue you have at hand. Now, what probably isn't obvious from all of this is that we can also, from each of these platforms, measure the composition of the air. So we started out with that simulated bioterrorist act that we all hope we never live through, or none of our loved ones live through. So what's really important there is being able to measure airborne particulates. So with COVID, we've been very familiar that the droplets in the air can have an impact to us. So when we sneeze, this 6-foot social distancing, that's because when you and I talk, we don't mean to, or we don't realize, but we're actually spraying things out to about 6 feet. They're tiny little droplets, and you can actually photograph them. But when you or I sneeze, we go out like to 27 feet or more with the speed of a baseball or higher. So this is like a real spreading event. So there's many of those particles, some of them are larger, but some of them are really small. So the COVID virus is around the size of 0.1 micron. So something that's at 0.1 micron, it goes really deep down into our lungs, as deep as they can go. And it can get across into the bloodstream, and from the bloodstream, it can actually get into the brain. So that's not just COVID. For example, we have this epidemic in Alzheimer's, and it seems that the particulates in the air can get into the brain where they cause inflammation, and then that inflammation is part of the whole Alzheimer's. So because the goal of this, you remember in our name, MINTS, the M was multi-scale and multi-use. Each of these platforms that you see in this robot team, they're not just looking at the composition of the water and the remote view down, they also all have a package measuring the size distribution of airborne particulates every second. So they actually work at the megahertz timescale, so 1,000,000 times a second. They're counting individual particles and sizing them. And so each of these three devices so the guy you saw the picture of there with everything on, he was just about to go into a live fire range. So this was something with special forces, and this particular range now, they're duplicating it for the bodyguards of the president, the Secret Service, to train them. So maybe I will digress on that for a moment. So imagine you have a V, and at the head of the V is a mirror. But this mirror is actually 3 plies of plastic, so that if you shoot a bullet at it, the bullet goes straight through it and it self-heals behind. So in these 2 parts of the V which come to the mirror, so if you're in one part of the V, you're actually looking at the mirror, and the person in the other part of the V looks like they're in front of you, but actually they're by the side of you. So in one arm of the V, you would have a role player that's having some training, like this guy, and he or she has live rounds. And in the other part of the V, you would have the actors that, so in this stuff with special forces, there were all kinds of scenarios that were very real to life. And I'll save some of that for later because I have a picture of the guys. Anyway, so it turns out in that situation, from the biometric response, we can actually reproduce the instructor's grades. So often there's not enough instructors for these type of things. Like if you think of school shootings or other shootings, there's a real need for better live fire training, because it's one thing to shoot at a target, but when someone sticks a gun in your face, you go into an entire different mode, which you will never go to when you're just doing target practice. in this example, we were using these results to actually tell us the composition of the environment around us. So remember the whole preemptive protection idea? So each of these different examples, so here we have multiple networks of sensors across DFW, and each of these color-filled symbols is the concentration of airborne particulates being measured in real time. You see the winds going over, and then these colors are the weather radar, so they can get rained out, for example, and the black dots are sources from permitting information. So each of these different applications, while they're doing their own thing, they're also all measuring airborne particulates, and we're even doing it from space. So this little video here, the color scale is the abundance of the airborne particulates in the air in micrograms per cubic meter, and this red plume you see is coming from the fires in California. So, you know, these fires, they produce so much smoke and particulates that that plume doesn't just stay locally, it like can sweep across the country. So back to the challenge I was trying to give you is to think in the problems you are addressing, how can you augment what you're already doing with a context? Because that context can be really critical. So supposing we're over here in Texas and we're in our rooms, and so let me take a side step. So the IQ, I don't know if you know about it, it's probably one of the safest places to be in a pandemic, because that building is equipped with a pathogen defense system done by some company called ActivePure. And so when it's been deployed, for example, in hospitals, the staff absenteeism rate has dropped by 44%. So imagine now you are a nurse or an ER doctor, someone comes in that isn't feeling very well, and even if you have a mask, you know, they're naturally huffing over you. And so those pathogens, unfortunately, sometimes the staff will get sick, right? So that then jacks up the staff absenteeism. So when they deploy this system, that staff absenteeism dropped by 44%, and there was no airborne infections in the ER since it's been deployed. So, you know, it was at a very high level before, so even some reduction is good, but so far there's been no event. So it all comes back to the quality of our environment. Like these things we don't see are impacting us. And the other thing to point out is it also affects our cognitive performance. So you and I, we all love to feel sharp. We want to be at the top of our game. But sometimes we have like a fuzzy head day. And when we have that fuzzy head day, we don't really think air quality. You know, that's the lie. It wouldn't even cross our mind. But in study after study, it's been shown that our cognitive performance is impacted by the quality of the air we breathe. So, for example, think of an incubator space. There's lots of inventive people wanting to be at the top of their game. It would make sense to make the environment there the best it can be and to be measuring it. So these guys are some of the students that were mentors for many of the senior design projects, and they're actually putting up a device in South Dallas, and we make all of our data open and the design's open. And this particular device led to the shutting down of an illegal dump called Shingle Mountain, which you might have heard about. So it's back to this sensing in service of society. Okay, so it's really exciting for me that we can use our sensors in multiple contexts together, because it's like different pieces of the jigsaw puzzle. So actually, just this part with the senior design students, this was entirely designed and built by them. And for the sensors, it's more than 100 students have been involved in that over the past 4 years. Okay, so at the heart of everything we do is the intersection between these three things. You've seen observations of many different kinds, from satellites to the wearables, to the robotic teams, and everything in between. And then simulation. But to do a simulation, you actually have to understand all the processes involved. So normally that's done with what's called a deterministic model rather than an empirical one. So that would be a set of equations that describe your system, the chemicals reacting with each other, the flow of the air, whatever it is. But it's an obvious statement, we don't understand everything, right? So for those cases where we don't have a perfect understanding that we can write a deterministic model, the machine learning can be really helpful because we can learn by example. Now, another interaction between these two, between the observation and the simulation, is something called data assimilation. So that's very powerful. So I grew up in England, and in England, they laugh about the weather forecast because they're normally wrong. And the reason they're wrong is it's really challenging to do a weather forecast. So let's just explore that for a moment. Imagine you were going to do a weather forecast. You would first want to discretize the entire atmosphere. All right. So you would have a latitude grid and a longitude grid. And say you were to have a 1/4 degree resolution for that grid at just one level, but you wouldn't think one vertical level. You'd typically have like 90 levels in the vertical, from the surface of the Earth up to the upper stratosphere. So the number of grid points is of the order of 10 to the 9. But each of those grid points, you have to initialize with a whole set of parameters, say as the weather, the temperature, the pressure, the wind speed and direction, and then a whole set of other parameters. So even if you had the world's best model, if you started with unsuitable initial conditions, you wouldn't get a good simulation. So the last quantum leap in the accuracy of weather forecasts was data assimilation. So the way data assimilation works is you and I have probably all fitted a set of points to a straight line. But now, if instead of it's just a univariate thing, imagine it's multivariate. So if you say that the atmospheric state, there's a whole set of parameters, like we said, temperature, pressure, humidity, but then, there's many more than that. So you have to specify those for each grid point. So imagine now you do a fit. Instead of to a straight line or multiple straight lines, you fit to a model that's describing your system, your actual weather forecasting model, your deterministic model. So what data assimilation does is it brings together all this data from satellites, radio sondes, surface measurements, and then does a multivariate fit to give you an optimum set of initial conditions from which you can start your simulation. So in 1995, we were the first people to do this for atmospheric chemistry. So in that case, if we go back to the environment where you have reactive chemicals, so for this company Active Pure that are looking at the indoor air quality, we're in the process of setting this up, that we're actually measuring hundreds of things, every second in many cases in the air, different chemical compositions, the aerosols, their size, their shape, the light intensity. So I don't know if you've ever thought of that. If you were looking down at the planet from above, and instead of having our regular visible eyes, you had eyes that could see chemicals. So there's some chemicals, like from the tailpipe of our cars, if we don't have an electric car, obviously, some of the chemicals that come out are like NO and NO2, nitric oxide. So if we had eyes that saw nitric oxide, you would actually see a line running across the planet if you're observing it from above. And that line would be the day-night line. So on the nighttime, because NO is so reactive, it immediately goes to 0 if sunlight isn't producing it. Whereas, so in this room, when we turn the lights on, turn them off, the whole chemistry in the room changes. The light is an energy input that drives the chemistry. So not only are we measuring hundreds of things in the air in real time, we're also measuring the spectrum of light, in fact, at 4,000 different wavelength intervals, that is then just driving the chemistry itself. And then we're fitting it to a model describing that with like 4,000 chemicals in it and 15,000 reactions. So to solve those ordinary differential equations, for the longest time we've had solvers, but more recently there's been things called physics-based machine learning. So we can use machine learning to solve that faster, but then also infer missing reactions. So there's normally always things that are missing that we're not describing, but the physics-based machine learning systems will help us infer those missing processes. So this is really a very tight-knit community by bringing together the simulation, the observation, and the machine learning. I'm running out of time, aren't I? So for the biometric stuff like no canary has to die aspect, we were learning that signature, the fingerprint in our body's response and how that maps onto what's in the air. For the boat and the aerial vehicle, we were learning the mapping of the fingerprint of the hyperspectral image with those stack of different colors we're observing to the composition of the water. So you can see this is a very flexible paradigm that you can use in a variety of cases. Oh, yeah, so one other thing we're doing, so you've probably seen on a CSI movie or that type of thing, there's a picture of somebody's tag and you can't quite read it, or there's a face and it's a bit fuzzy, and they'll say enhance that, and then automatically you see who the person is. So for the longest time, that was really a bit of a joke, but now it's actually for real, and it's called super resolution. So we are using that super resolution for a variety of things. In fact, I forgot to show this picture on this image. Okay, so what we see here is it's a very low resolution, so it needs super resolution of that, I guess. But if that was a bigger image, what you're seeing, we could see from space, 600 kilometers in orbit, a leak in valve on the UTD campus. And the way that works is, if you or I were to go outside, say you go out your front door in the morning and you see your yard, if it looks nice and green, you know the grass is probably doing well, it's well watered. And that green is coming from the chlorophyll absorption in your grass. But if the grass is under some water stress, and maybe it's been under some water stress for a while, it's looking more yellow and orange or whatever brown color it's got. So we subjectively just know instinctively now what that means, all right? But from space, we also can observe the whole spectrum of light. And so we can actually quantitatively look at the ratio from one wavelength where chlorophyll absorbs to one wavelength where it doesn't. And that is a very good metric of the water stress. So the reason that's important is the population of Texas has been growing by 1,000 people a day since 1990. Our reservoir capacity has not increased for 35 years. The one that's just come online, is not completely operational yet, corresponds to less than 1 year of population growth. And we will not be able to have another reservoir for another 35 years because of the whole regulatory permitting and other process. So in 2011 to 2015, you may remember we had actually quite a drought. And on top of that, on average, 18% of our water at least is lost between the reservoir and the consumer. But Richardson, like many other cities in this area, have an aging infrastructure. The pipes under our roads are typically 30 to 40 years old. And so the older infrastructure gets, the more likely we are to have leaks. So any help we can get in identifying where things are leaking that we might not have known for other reasons can be really valuable. And if you think of the environmental change we've seen, the average warming of the planet leads to extremes in the cold and the heat. So, and it also leads to specific drought patterns. So if you look at every single drought we have had, it's always been in a La Nina phase. This El Nino La Nina phase. And what that means for us is in the La Nina phase, the jet stream that normally brings water that it rains on us gets pushed north and it rains on somebody else. So those events are going to, in all likelihood, I don't enjoy saying this, they're going to get more extreme, and our need of caring carefully for our infrastructure and our water usage is going to improve, which is an obvious application for IoT. But it again brings us back to this use of sensors. It's not just the in situ sensors looking at one location in our yard. We can actually see from space the entire yard. We could see from our security cameras that have the near infrared and the red band, we can actually do the same thing at a sub-centimeter scale across individual beds. So I would just, as a personal satisfaction is why I'm saying the challenge, think of how you can bring together for your applications more data, because it can help give you much more satisfying holistic solutions. So how many minutes do I have?
You can go to 9, 10, and then we'll
Yeah.
have a.
So I probably, let me leave it here, because if you guys have any questions, I'll do my best. to
Yeah, we can
answer.
do Q&A now for the next 10 minutes.
Yeah.
Who built the robot dog?
So the famous one is Boston Dynamics, right? So this is not Boston Dynamics, it's Ghost Robotics. They're actually much more affordable, but they have another really cool thing. Every motor is also a sensor. So they're monitoring the current, which is obviously related to the torque,
Mhm.
and they use that so the robot actually feels its way, which is very cool. So the payload that this robot in this case is carrying is which you can see there, is the air quality one, which we also have the same payload on the boat and the aerial vehicle in this case. And so
It's the doors locking.
this,
No, that's literally what it
the
was.
boat can go unmanned for 20 hours autonomously, and there's a bigger sibling, which is a full ocean going one, which can actually go for about a month. They were built in Norway. You know, I guess they grew up, the company is really lovely to deal with. They grew up around the oil and gas industry. And the aerial vehicle is built by a company called FreeFly for movie making. So if you've seen movies like Venom and so on, they were actually filmed from that platform. So we built our own landing gear and put our camera on it. So it's a beast. It's like really big.
The drone.
Yes.
Yeah. It's cool.
So I don't normally use drone, not because it just has the connotation of someone's going to get killed. And so I want to keep people alive, so I call it aerial vehicle. Yes, yes, sir.
Quadcopter. How about that? Quadcopter.
Yeah,
Maybe that's not a quadcopter.
that one is, yes.
I was interested in your comment about the submicron particles going across the blood-brain barrier and stimulating Alzheimer's. So that's any kind of particulate, whether it's from a forest fire or a chemical or
Well, the
a cement
size,
plant?
it's like a Trojan horse. The size is what lets it get across
Right.
the blood-brain barrier. The effect it has will depend on the composition. So I'm grateful to also have an affiliation with the Brain Health Center. So that UTD has another facility next to UT Southwestern and the medical district. And there they have two really nice images, fMRIs, and they actually can see this inflammation. They like image it and characterize it. So yeah, it's unfortunately it's for real.
Can you go in there and get imaged and see?
Yeah, you can do. Absolutely. Yes, sir.
Does everything operate autonomously together, or do you have to pilot each one individually?
So we did this on, it might look very fancy and so on, but we did it in a really small budget. So the software that guides this is actually open source. And so what you do is you draw a map like a polygon, and then it can go and survey that area. So then what we do is we export that flight path, and then we import it in the control software for this. So the boat will actually go underneath exactly the same area. So that careful coordination is really important. So this and this are fully autonomous. This one, it could be fully autonomous, but it was actually being someone with joysticks was controlling it. And one of the uses a lot of this is not just above ground, it's also subterranean with all the tunnels. So, yes, sir.
What kind of bandwidth do these guys need to operate, and what networks do you have there? Seems very remote.
Yeah, so because the idea here was Lego blocks, the various blocks could be substituted. So with the small pot of money we had, the network that connects all of these is actually a long-range Wi-Fi using ubiquity and long antenna. So this can go up to about 1 kilometer. But you could easily switch it out for any other communication system as long as they can talk to each other. Great. Yes, sir.
So as far as the hyperspectral analysis, are you doing that at the sensor itself, or?
Yes. So maybe I should see if I can't remember what pictures I have here. I could give you. Oh, by the way, while we're getting there, that's the sneeze, a real photograph of the sneeze. Yeah, here we go. So this is actually a visualization of an actual hyperspectral data cube that was captured. So this is collecting imagery at some phenomenal rate. So there's actually a solid state disk on the camera, and the processing computer is right next to it. We mount the disk on the first camera on the processing computer, so we don't need to copy anything, we just read it. So that happens on the fly on board.
Are you doing fixed point or multiplanar?
Sorry, sir.
Is any of this technology in production now?
So you can actually come and see it in the IQ. So we basically use all off-the-shelf items, and our part is really in the software and how we put it together.
Yeah, the reason why I asked is back in 2006, when I was Chevron about a project for hyperspectral analysis
Okay.
to detect H2S or hydrogen sulfides. That's the number one killer in the world.
Okay.
And so they couldn't, back then they didn't have edge computing. So they actually sent all that data, which was virtually gigabits and terabytes.
Yes.
To the computer.
Absolutely. So we couldn't do this if we had to have the communication. So like even in the military context, often they will do it after they land. So we didn't want to do that. We wanted to do it in real time.
I guess so. My point is now, since 2006, that's 6 years.
16.
Number of years. Basically, the technology has advanced so much.
Yes.
That is now a market for more hyperspectral analysis, turn the gas for methane and.
Absolutely. So for the methane, they're even doing it from space.
Correct.
No.
Yeah, and the problem was back then was the spectrum for hydrogen sulfide. They couldn't quite dial that in. But I imagine with the technology we have today, and computer processing, the AI and the ML, you're able to do that.
So our choice of the spectral region was driven by the limited funds we had. So this camera was actually $60,000, and it goes from the UV to the near infrared. For many of the chemical things like the methane and so on you were talking about, you would really need to be out in the infrared. So you can also get hyperspectral cameras in those wavelength regions, and also it would be really good to have a synthetic aperture radar. So the radar looks at texture. So for example, for the oil spill, the wave height is affected by having oil on the surface. It changes the wave height. So you can actually see that with the synthetic aperture radar. So, and back to the irrigation example I was showing you, The visible part of the spectrum is blocked by cloud, but the synthetic aperture radar sees through the cloud. So you can actually reproduce the visible images from the synthetic aperture radar images. So cloud coverage, and so losing that part of the imagery is a major issue, because at any moment, a significant part of the planet is covered by cloud. So being able to see through the cloud is really very helpful. Yes, sir.
But do you see the Project Owl solution as adding a larger network capability to your solution?
Say that first.
Okay, remember Project Owl with Brian Naus?
Oh.
Right. So do you see his solution as giving you ability to cover a larger area?
So I guess the best way to think of that is this Lego block example. So what Brian is doing with Project Owl is the communication blocks, he's giving some alternatives for that. So that certainly does help with the deployment, yes. Yes, sir.
So, what kind of algorithms do you use in your modeling?
For which in particular?
I see a lot of computer vision here. So do you just deal with the computer vision for the imaging stuff, or the kind of textual data? Or...
Oh, so, okay, we do actually a very large range of them. So, oh, by the way, this one was looking at breath analysis. Do you know the composition of your breath it can tell you all kinds of things, like you could get your blood sugar, the early onset of, like you have these dogs that can smell cancer from the breath composition. So that's another area we're doing. So for the EEGs, this is from the eye tracking glasses. They actually have a camera in there and a microphone. So at the same time as we were measuring the 113 parameters 500 times a second, a very small subset of which you see visualized here. And here the activation, this area of brain activity is associated with active listening, this with motor control. So you can actually understand the different activations. At the same time, we were turning the audio into text with machine learning. And then you could click on any word and it would jump you to all the biometrics. Wow. So for example, if you use the personal pronoun you, it will attract your attention. And that's very significant. You can actually see it in the biometrics. Somebody uses your name, like many times in sales, people will use someone's name because they know it attracts their attention. You can actually see that. So it's from image processing with the super resolution and those parts to the natural language processing and all kinds. Not just super resolution, we also use these things called super learners. So you don't just have one machine learning algorithm, you use multiple approaches and then you stack them together. So it's the learner of learners. Wow. That makes sense. Anyway.
Yeah, Dale Carnegie teaches that someone's name is the most beautiful word in the world.
You actually can see it, it attracts their attention.
And it's for
Let's keep talking to Lary.